Let's see some examples for kernels and images. Right now we work with matrices mostly. So let's have a matrix A with entries 1, 0, negative 2, 3, 1, minus 9, minus 5, minus 3, 19, 5, 3, minus 19. So this is a 3 by 4 matrix. That means the associated linear transformation TA maps from R4 into R3. Since we have 4 larger than 3, automatically we'll have that this cannot be injective, and that means that the null space, for example, will have dimension larger than 0. It will be dimension 1 or larger. So let's find the kernel or null space and rank. So this is the same as the dimension of the column space, but then we might want to separately find the column space itself. So we will use reduced row echelon form of A. For that we have to do row reduction. We have the first pivot 1, 3, minus 5, 5. We don't have to do anything with the second row because under the pivot we already have 0. In order to get 0 from minus 2, we have to multiply the first row by 2 and add it to the third row. So then we get 2 minus 2, 0, 6 minus 9, minus 3, minus 10 plus 19, 9, and 10 minus 19, minus 9. Then we continue to the second row. This is the pivot. We make under and above entry 0. So for the first row, we will have the first row minus 3 times row 2. And for the third row, we'll have third row plus 3 times row 2. Then what we get is 0 in the 1, 2 entry. Then we are subtracting 3 times the second row. So that will be plus 9 minus 5 is plus 4. And then minus 9 plus 5 minus 4. The pivot second row doesn't change right now. Then the third row, we make this second entry in the third row 0 by adding 3 times the second row. No, I'm sorry, minus 9 plus 9 is 0, and 9 minus 9 is 0. And then we cannot continue to the third row because it doesn't have any non-zero entries. So this is the reduced row echelon form of the A matrix. The column space of A, it's the columns, pivot columns, but the pivot columns from the original matrix. So don't confuse this, that the first 2 columns have the pivot entries, but what we need is from the original matrix the first 2 columns. So this will be, the column space will be the span of the first 2 columns, 1, 0, minus 2, and 3, 1, minus 9. So we also see that the rank and the dimension of the column space is 2. Then the null space is coming from the free variables. So for the null space, let me remind you that the null space of A is all the x vectors such that ax equals to 0. So for this, basically, we have to solve this homogeneous equation, and for that we also use the reduced row echelon form, because then the reduced row echelon form says that 1 times x1 plus 0 times x2 plus 4 x3 minus 4 x4 equals 0, and the second row says 0 times x1 plus 1 times x2 minus 3 times x3 plus 3x4 equals 0. So we can solve for the pivot variables. Of course, these are 0 terms. And we have x3 and x4 free variables. So from the first equation, we get x1 equals minus 4x3 plus 4x4. And from the second one, x2 equals 3x3 minus 3x4. Let me also write down that x3 is just x3 and x4 is just x4. I want to write it aligned in one column. And then I also write here that this is plus 0 x4 and this is 0 x3. Because then the solution vector for the null space, which is the same as the homogeneous equation, is if you collect these, so this is x1, x2, x3, x4 components, and what we do is collect these columns, x3 times minus 4, 3, 1, 0, plus x4 times 4 minus 3, 0, 1. And since x3 and x4 are free variables, they are arbitrary. We could replace them, if you don't like this x notation, we could replace them with c1 and c2 to see that these are linear combinations of these two vectors. So what we have is that the null space of A, or the kernel of A, is the span of these two column vectors. And we see that this has dimension 2. All right, so what else can we say about this? So we have a map from R4 to R3. We also see from here that TA is not injective. If you look at the image, the dimension of the image of the transformation or the matrix, we found that the column space or the rank is 2, and this is less than 3, which is the dimension of the vector space into which we map. So that means this is not surjective, not onto. So this means that the picture is that we have this R4, we have R3, and this is into, not onto. And also the kernel is not just the 0 vector, it has dimension 2. So the interesting question is then, how can you find a vector, a B vector, which is not in the image? So if B is not in the image, then that would mean that AX equals B has no solution if B is not in the image, because the image means that all the vectors that can be written as A times X. Well, how is it that we don't get a solution? How would we try to solve it? Well, the way we try to solve it is that we put together A and B into an augmented matrix, and then we do Gauss-Jordan elimination to get a reduced row echelon form. But we already know what the reduced row echelon form of A is. The reduced row echelon form of A has the first two rows are pivot rows, and I don't really care actually what we have here in these entries, and then the last row is 0. And then we're supposed to do this row reduction with B, so we're supposed to have something here, here, And if there is no solution, then what you see from here is that the last row could give problem with a solution, because this says that the left hand side is 0, since all the coefficients are 0, and then what we need is that the right hand side is not 0, so this shouldn't be 0. Well, while we do the row reduction, these entries affect the third row unless these were zeros originally. So one example for this right hand side vector b would be, if we start with, for example, b equals to 0, 0, 1, because then while we are doing the row reduction, these zeros never change, since we are multiplying and adding together zeros. And that means that this 1 wouldn't change either, because we would be adding, during the row reduction, we would be adding zeros to it or subtracting zeros. So this will not change during row reduction. And also this creates a case where there is no solution, because the last row would say that 0 equals 1, which is impossible. So that means this is not in the image, the linear transformation, or, which is the same thing, the column space of A. We have also an example or an exercise in the homework set where we have a transformation written as x1, x2, x3, x4, x5 equals 7x1 minus x2, x2 plus x3, and let's say x4. So then what this says is that this goes from R5 into, because there are 3 entries in this vector, R3. The fact that this is row vector shouldn't matter. It's just a different way of writing the notation. And then to write it in a matrix form, so we would need a 3 by 5 matrix. And what this says is that the result should be the vector 7 x1 minus x2, x2 plus x3, and x4. So how do we get this? With matrix multiplication, we must have 7 in the first entry, so that we get 7x1, and then minus 1 in the x2 entry, then 0 in the rest, and we need 5 entries in the first row, or in each row. For x2 plus x3, to get x2 plus x3, that should come from the second row. We have 0, 1 x2 and 1 x3 and nothing else. And then for the last row we have 1 in the x4 column. So these columns represent x1, the coefficients of x1, x2, x3, x4, and x5. And then from here, then we can just work with this A instead of the T transformation. So we will come back to abstract vector spaces later, in a few sections later. Right now, I just want to show a simple example where the transformation is the derivative operator. We can differentiate many different functions. Let's choose now P2 polynomials, so degree 2 or less polynomials. So if you differentiate the second degree polynomial, you get a first degree polynomial. That means this is a linear transformation from P2 to P1. P2 has basis. The standard basis is 1x x squared if you use the x variable notation. since a general vector could be written as a0 plus a1x plus a2x squared with some coefficients a1, a2, a0, real numbers. So let's consider this over the field of real numbers. This also means that the dimension of P2 is 3, since it has basis with 3 vectors. And if you are not comfortable with this constant, let me write this as a0 times 1 to match the basis element. So then what the derivative does for arbitrary element P from P2, dp, when you apply d to the polynomial px, that means that we have to differentiate a0 plus a1x plus a2x squared. What we get is a1 plus 2a2x, or if you want to see the basis elements, let me write a1 times 1 plus 2a2 times x. So these are the basis elements, and then a1 and a2 are arbitrary. Then also 2a2 is arbitrary if a2 is arbitrary. So this shows that the image of this derivative operator, or linear operator, or linear transformation, all the polynomials in P1 such that Q can be written as the derivative of P for some P from the degree 2 or less polynomials. And what we can see here is that this is like a linear combination that we got here. So that means you can get all these vectors as a span of 1 and x. And that means that the dimension of the image is 2. So D is from P2 to P1. P1 has basis 1 and x, the degree 1 or less polynomials. So that means the dimension of P1 is also 2. And because these two numbers are the same, that means that D is onto or surjective. Then if you want to look at the null space of D, that's all the polynomials from P2 such that derivative takes it to the identically zero polynomial. So for that we see what this dp of x looks like. How can it be 0? We already have a formula for that. It's a1 times 1 plus 2a2 times x. So this is identically 0. This is a general theorem for polynomials, that a polynomial is 0 only if all the coefficients are 0. So that means a1 is 0 and a2 is 0. But p was a0 plus a1x plus a2x squared, and we only found that a1 and a2 must be 0. So that means a0, so this is supposed to be point to a1. a1 and a2 are zeros, so a0 is arbitrary. That means this p of x polynomial in the null space has to have the form a0 plus 0x plus 0x squared, which is just a0 times 1, which means that the null space of this D linear transformation is spanned by the basis with one element, the identically one polynomial. And since this is then the dimension of this null space or kernel is larger than 0, that means D is not injective, which means it's not one-to-one. How can it be not one-to-one? Well, think about this, if you differentiate the polynomial, for example, 3x plus 2, you get 3. And this is the same as the derivative of, for example, 3x plus 9, since the constant goes away. So you have two different polynomials that have the same image. That means it's not a one-to-one map. So again, we will come back to this later, to abstract vector spaces, when we have a little bit more tools to handle them.